But in any case, thank you very much indeed for giving me this wonderful opportunity, Sushanta. I thank you very much for your kind invitation. Well, today I would like to talk about specifically the spintronics at the nanoscale, enabling green information processing. But before that, I would like to give you a brief introduction about Tohoku University itself, because I think Sushanta's mind, his mind, he wanted us to collaborate in the future. So I would like to show you what kind of university we are, and what kind of university we are, and as you can see, my next slide shows a map of Japan and where we are located. We are located in the city of Sendai. Is it possible?
Because they're recording something challenge disclaimer. So because they're recording, it's a little bit challenge.
Oh, okay. All right. So we'll see how it goes, because I tend to forget what I need to speak. But here it's obvious. We are located 300 kilometers north of Japan, in the city called Sendai here, with 1 million population. Very quiet city compared to Tokyo, for example. It has a much larger population. We are established back in 1907 as a third national university in Japan after Tokyo and Kyoto. And we are proud to be the first university that accepted, at least in Japan, female students back in 1913. So we have three tenets: research first, open door, and creating a social value. And I'd like you to give a sense of how the scale of our university. So we have 18,000 students, 8,000 of them are graduate. We have 3,000 faculty and 3,000 staff to support all the activities, including education and research. And our annual expenditure is about 169 billion Japanese yen, which converts to slightly more than $1 billion US. So this is the size of our university. We are enjoying a reasonably big number of granting aids for scientific research, which is equivalent of US's NSF grant, and also we get from private industry similar amount support or joint activities. So that's what we are doing, and on science side, this is partly history, partly today. Back in 1916, our 8th president, Kotaro Honda, invented this KS steel, and that was world's strongest permanent magnet at the time. And since then, there have been, well, depending on how you count, but 5 generations of hard magnet, and but 3 of them are invented by our faculty or our graduate student or alumni, basically. And the current strongest magnet, niobium iron boron, was invented by Masato Sugawa. He got the PhD from Tohoku University. And these hard magnets, all you know, it forms a basis of electrical vehicles or wind turbines and actuator for robots and so on and so forth. So it's a foundation of today's science and technology, and particularly making the world greener. Okay, and The other thing that we have on our campus is next generation synchrotron light source, which is open to everyone. And here we used to, well, we still have Spring 8, which is for hard X-ray, but we were lagging on this soft X-ray region. But now with Nanoterasu, we have a very strong and light source with the capability to focus it into nanoscale. So using this Nanoterasu on campus, you can do spatial, temporal, element-specific analysis of what's going on in the material. So that will give you a tremendous opportunity to for your various fronts for your research fronts. I'm not sure how many are interested in how to build those or how to finance those building costs, but this one, half of them come from the government itself, but half of them we formed an alliance, including Tohoku University, to come up with the total cost, which is approximately $380 million. So we had to come up with well, somewhere around $180 million. And for this, we divided the beamline time into small chunks and sold this 10-year right to have 200-hour per year beamline time for many industries. And we succeeded in getting more than 100 industry to come to this, to invest in this opportunity. So this means two things. One thing, of course, that we succeeded in getting the finance involved from the private industry, private sector. And also this is a platform for industry academia collaboration. So when you come to this Nanoterasu, there's already more than 100 companies around, and they are looking for new possibilities and new ideas. So naturally, this will become, and this is becoming a platform for industry academia collaboration. All right, and for your information, we have 28 beamlines, if I remember the number correctly, and we are only using 10 of them. So there are remaining beamline that if you have enough funding, you can install your own beamline. And that costs you approximately $10 million. But if you have $10 million, you can have your own beamline installed here. So I'm looking forward to proposals on this front. And the facilities are widely distributed. Unlike here, you have a very concentrated, nice collaborative atmosphere facility, but our facility is distributed all over the campus. This is your synchrotron radiation, which is actually operated by National Lab, but we did contribute to funding and all those things, construction. And we have cutting-edge core facilities, including cryo-electron microscope for materials, as well as medical applications. Here we have a unique Tohoku Medical Megabank facility, which has a cohort study of 150,000 participants. UK Biobank has 1 million participants, so it's much smaller than UK Biobank, but we have coherent participants. Many of them are are still there after 5 years and 10 years. So we asked them to come and check up their status, and most of them are very willing to support this activity. So we can keep track of this, most of the 150,000 people, what's happening in their lifespan. And also 70,000, out of 150,000, 70,000 participants give us a 3-generation cohort, meaning that mother or father is a kid and grandfather or grandmother. So that will allow us to go deep into what might happen in those line of generations. So this is not easily find. You cannot find easily this 3-generation cohort. UK Biobank wanted to do this, but later abandoned it because people didn't trust that much of the cohort system. So this is probably the only cohort with 3 generations. And we have a semiconductor co-creation platform distributed, but if you add all of them, we have 8,500 square meter clean room facility, which is largest in Japanese universities. And we are making a number of interesting research efforts, and here collaborating with 450 industry partners. And of course, we have superconducting systems that support the huge data generated by not only from the Nanotechnology, but also from the Tohoku Medical Megabank and so on and so forth. So data handling and data, well, basically data is a source of the new value, and we are aware of it, and we are expanding this superconductor systems. Okay, so so this is the last slide of my university introduction, but we have recently became the first university and only university that's being supported by the new university supporting scheme called University for the International Research Excellence Program. Japanese government set up in 2023 10 trillion yen university endowment fund, and the outcome of which is going to be used for selected research universities, supporting selected research universities and part of PhD students. And they solicited applications. Tohoku University was the first to be approved and making eligible for the additional support. We are on the second round of selection. I'm on the selection committee, and I spent the entire week last week on the selection committee site visit and so on and so forth. But there will be additional universities. I cannot say which one will become the next, will be supported by this program, but this is quite a substantial program in a sense that it will support university for the next, at most 25 years. So that's extremely long time. And the additional funding is matching fund. So it will give you, if you are earning a certain amount of billion yen from non-government sources, they will match this non-governmental income. So we are getting this year more than $100 million from this new scheme because we are getting non-governmental sources of approximately this amount. So that will allow us to enhance our university-wide activities. There's no string attached, so we can use more or less on many fronts of education and research on on the university activities. So that's what I wanted to say, and I hope, well, many of you are not president of university or not terribly impressed by the numbers here, so I will let me jump into the scientific part. Okay, so spintronics. I've been working on spintronics since back 19. I hate to say this, but 1988, so quite a long time. And there are many collaborators here and many agencies to support the activities. But let me just give you a brief overview of what I've been involved in spintronics research. Well, the idea here, at least the modern idea, why we need this spintronics approach is because of the energy. Here we have energy production, world's energy production, which is somewhere around 5 times 10 to 20th joule per year, and it's gradually increasing approximately 2% per year. So this is not for compute, but this is for all our activities. Energy production is somewhere around here. And if you just extrapolate what's happening today for compute, and then this is the trend here. And if you don't think anything and just extrapolate it, it will cross the world energy production at slightly beyond 2040. Of course, this will not happen. We want energy for other activities as well. So in realistic or maybe quasi-realistic projection done by SRC, Semiconductor Research Corporation in US, gives this one, but this is also too optimistic. I mean, we still need a lot of energy, unless we get all of a sudden a huge energy source from fusion breakthrough, or we need to be wise enough to use those energies that is now being used in compute. So reducing energy for compute is quite a challenge and also necessity for the next generation of society and next generation of humankind. So let me just tell you a bit about 4 things. First is impact of spintronics non-volatile memory. Then I will discuss about spin physics and scalability of magnetic tonal junction, which is a spintronic device that gives you non-volatility. Then I move on to probabilistic computing with stochastic junctions. Stochastic junction means here we are talking about non-volatile memory. So once you set your memory in one mode or remembering one thing, it will stay there for more than 10 years. But we can engineer things in such a way that the memory will go back and forth within, let's say, 10 milliseconds or 1 millisecond. You might think that will not, well, we don't call it memory anymore, but it will not be of no use. But we show that you can use it to make probabilistic computing, and that can solve a number of problems that is difficult for usual digital computers. And on the materials front, I will just give you a brief overview of what we've been up to, hopefully advance the field further on. Okay, so the first impact of spintronics non-volatile memory. The reason why they spend so much energy is partly because the memory that is currently available, current working memory, are both volatile. SRAM volatile, DRAM volatile, so you have to keep the power all the time in order to keep your information there. And that becomes a huge energy sink in a sense. And for example, in this case with high bandwidth memory, they're using DRAM on top, right next to CPU, and this is your GPU configuration. And usually what happens is that because you use so much energy, the temperature goes up, and DRAM has to have a refresh because charge is gone every second. And so every once in a while you have to read and you establish the content in the dynamic random access memory. And that refresh rate will be shortened if you increase operational temperature. So it's not terribly easy way of doing things, but this is memory that has high density and can stack on each other and so on and so forth. So that's what we are relying on in your, let's say, NVIDIA chips, okay, which is shown here. All right, but so what we are doing here is that we are working on a chip with all the lights of rooms on, because if once you turn off the lights, all the contents which you stored in the room is gone. But ideally, what you would like to do is to turn on all the rooms that you need to do, but keep other rooms dark. You don't want to turn on those unnecessary rooms that you're not going to use. So this type of operation will be allowed if you have a good non-volatile working memory. So these are the candidates of working memories. This NAND flash is not a working memory, but this is a great memory. You have 256 gigabytes of your memory in your smartphone, and this is extremely nice memory, but it's in terms of bit per bit cost. But okay, I think my pointer is dying, so let me see if I can find mine. All right. Besides, well, some of you might know, but one cell can be rewritten only 1,000 times. Here, only 1,000 times. Well, that's a trade-off between making a bit extremely inexpensive, but you don't store your photos on your flash memory more than 1,000 times. So this is very reasonable. But working memory has to work with your processor, and the processor can go up to 1 gigahertz, which means 10 to the 9 times rewrite is possible. So this endurance has to be much greater than 10 to the 9. And this spintronics, which I will go to explain to you, has reasonable high endurance, how many times you can rewrite. The write voltage is low enough, lower than the supply voltage, and write time and read time are reasonably fast, and non-volatility is there. So this is an ideal memory for replacing DRAM and SRAM. Okay, and we experimented it on various integrated circuits. So these were, we designed them, sent our data to a company that they can make 300 millimeter CMOS wafers, and we get it back. And on our campus, we have spintronic 300 millimeter lines. So we finished putting our spintronic devices on it. to see how things work. So early times, there were no tools for designing things. Many of you might know how people design integrated circuits. They sit in front of a computer and everything is ready to simulate and also design placing your devices according to your functions. But these were not available, so we had to go through all the processes, all the tools, inventing or establishing ourselves. So that was a somewhat interesting but painful part. But after that, we've been able to design a reasonably large circuit using our technology. And now you can go and buy those options in standard design tools. But here, the results are tremendous in a sense that when you only use CMOS or CMOS plus spintronics device, we can reduce the power by 1,000th, another 1,000th, 3%, and 1%. Well, it depends slightly on how you use those integrated circuits, but the power reduction is clear, and on AI associated memory chip, FPGA MPUs, and STT-MRAM and SOT-MRAM as well. So these are prototype and proof of concept integrated circuits that we've been showing to the world and reporting at conferences. Those magnetoresistive random access memories, particularly spin transfer torque magnetoresistive random access memories, are in the market and in the product already. So it's slowly getting into a product like okay, so this is not the one, like this one. For example, Sony designed a GPS receiver, and Samsung fabricated it, and Huawei put it into their smartwatch. And one charge allows you to use it for 2 weeks, because GPS, after all, is a very power-hungry part of your smartwatch. My Apple Watch lasts only a day, so I would love to see Apple employing spintronics technology, and we can forget about charging it for 2 weeks. Well, GPS is also a very important thing that you need to have in many, part of society. Self-driving or supporting where you are, which one got there, and so on and so forth. And even these days, we need for many military applications as well. So, and the overall market here is about 500 million, which is rather small, but it's rapidly increasing at the moment. Okay, so now some physics and scalability of magnetic tunnel junction. Scalability means how small you can make them, because the industry will not look into the technology that is not scalable, because the scaling is the principle that they rely on. Okay, so this is your magnetic tunnel junction. Magnetic tunnel junction is a very simple junction with 2 ferromagnets, green and purple, separated by a pinkish insulator, which has to be thin enough so that your electron tunnels through it. And that's the reason why we call it magnetic tunnel junction. And the resistance of this 2-terminal device depends on whether your magnetization is aligned in direction or anti-parallelly aligned. And usually this anti-parallel part gives you high resistance. aligned part gives you low resistance. So that's you keep your information there. And there's spin transfer torque switching, STT. That's why we call it STT, magnet resistive random access memory, STT. Beyond which, when you run current through it, there is a threshold current beyond which you can, depending on the direction of the current flow, you can set your alignment in parallel or anti-parallel. So you can write that way, and you can interrogate the alignment by reading the resistance. So basically, this is magnetic tunnel junction, how it works. Scaling, when energy of separating the two states, parallel and anti-parallel, against the thermal fluctuation, you have to have a certain energy barrier to prevent accidentally flipping one state to the other. And this energy is, this is flipping time constant, and energy is here. And so energy is some constant times a geometrical factor, in this case, volume of our ferromagnet. You can easily see that the current that you need to invest in order to change the state will be proportional to the stability of your state. So it's natural to see the current is also governed by this barrier height. If barrier is high and your state is extremely stable, that means you need to invest more current to change the state. So it's physically very straightforward. The thing that is not straightforward is when you have in-plane magnetization. When you put your ferromagnetic device on the thin film case, usually what happens is that your easy axis is on this direction, longer direction. What to precisely say it's in the diagonal direction, but for the sake of simplicity, let me say that this blue one is easy axis, the lowest energy part, and it's degenerate with left pointing and right pointing. So that's the reason why we have stable two states. So the energy barrier that separates the two states, it's governed by this yellow one, which is the second largest energy, and the red one is the largest energy because it gives you a huge energy barrier, but the protection here comes from the lowest energy barrier here. But unfortunately, when you try to change the state from left pointing blue to right pointing blue direction, you have to invest a very large amount of current because the physics here is a precessional motion of blue magnetization direction going through yellow and red. So you have to overcome this red part, which can easily be 100 times more than yellow. So it's inherently in plane is not efficient. Whereas in perpendicular case, these two are the same. So this is the reason why people wanted to show the perpendicular. But before 2010, it's already 15 years ago, people tried many combinations of materials and couldn't find the good ones because there were a number of requirements for integrated circuits. You have to have this, you have to have that, and you have to have all of them at once. So until 2010, this is our work. We showed that the switching current is low. This is perpendicular. The resistance change is reasonably high. We can go through annealing process, which CMOS people required, and so on and so forth. So and reasonably high barrier. And the interesting thing is here is that cobalt ion boron, MgO cobalt ion boron, when you're not in this business, how common these materials are. All the industry labs as well as university labs have these material sets. What was special about this report was to make these cobalt ion boron layers thin enough. Thin enough meaning 1.6 and 1.0, and which actually makes interface perpendicular anisotropy, which means the interface between cobalt ion boron and MgO becomes a dominant factor, which makes this perpendicular easy axis. So the reason why we found we were able to show this is because we did things in a very systematic way. Here we have 6 cobalt ion boron, which I don't explain in detail, but basically they are showing that they're in plane, easy axis. When you make it too thin, then it becomes super paramagnetic, no use for non-volatile memories. But in between, we found that there is perpendicular magnetic easy axis. So many people thought that this region didn't exist at all. And when you make it thin, then it just becomes super paramagnetic. And many people forgot about the interface properties. The reason why we did this is because this is completely separate material, so I don't want to confuse you. It's in the different era, but we've been working on ferromagnetic semiconductors, and we are trying to show electric field control of ferromagnetism, ferromagnetic transition. And here we wanted to make sure that our target material, indium manganese arsenide in this case, thin enough, because this is a conducting material, and we are using transport to show the magnetization behavior of indium manganese arsenide. And if it's too thick, then as you can easily imagine, the only part that responding to your electric field is only at the interface, and the bulk will not respond, and we will not be able to see this kind of clear thing. So making target material thin is critical, and of course this is at low temperature, 22.5 Kelvin. This is world first, but people want to do, including ourselves, want to see these things in metal at room temperature. We did succeed seeing this, at room temperature, but unfortunately, our report was preceded by a couple of groups, one group at least, that showing electrical control of ferromagnetism or magnetization at room temperature. The secret here is that the two things. On the electric field control part, many people had thought that you will never be able to do this, because think about how many electrons you have in metals. You can only change a very, very small amount of your electrons by applying electric field. And there's a limit in dielectric that you can apply electric field, let's say 10 to 8, 10 to the 9 volt per centimeter. And beyond which, there's electrical breakdown occurs. So there's absolutely no way you can see it. The thing that many people can see in this material system is that your anisotropy or magnetic anisotropy is governed by the interface property. So interface property doesn't reflect or rely on how much you have in the bulk, but how much electron you can control at the interface. And that's one reason why we see, and many others see, electric field control. Also, this perpendicular one, these are perpendicular magnetic tunnel junction variations. The perpendicular ones, I later learned that several groups have also seen this perpendicular nature in cobalt ion boron MgO system. All the reasonable labs have this capability of producing cobalt ion boron MgO. So two professors, I was surprised to learn this almost identical story about the professors later came to me after we published this 2010 paper that actually we saw this perpendicular anisotropy in my lab. A graduate student came to me and showed that somehow we got perpendicular easy axis on our system, cobalt ion boron MgO. And both professors told graduate students that it's impossible. So go back and do it again. So there's a lesson to professors that you have to listen to what the graduate students come to you and show you something unimaginable. So, but because we did things systematically, we are very sure that there's a perpendicular axis at very thin layer of ferromagnetic layer, and we can enhance it by using 2 interfaces, 4 interfaces, and so on and so forth. And we can go to, let's say, 10 nanometer type devices. And these are the completed version that people actually use, are using this stack of structure in their product, more or less. It looks complicated, and it is complicated. This is a recording layer, so the magnetization of the top layer becomes upward or downward oriented. The reference layer is complex because we are combining 2 ferromagnetic layers pointing each opposite to each other to reduce stray field that's coming out from this reference layer. Okay, and it's surprising that we can have 300 millimeter wafers with this 0.4 nanometer accuracy, on average at least, and have a good variation. Integrated circuits is all about variations. If you have large variations, you won't be able to make a circuit out of it. Okay, so the scalability. When we reduce our junction diameter below 30 nanometer, we see energy barrier decreasing a lot. So more than 80 E over KBT, energy barrier measured by KBT, more than 80 is usable on usually a number of applications, but below this, it will become problematic. And so we came up with an idea and showed that we can go up here above 100 or beyond 80. You can do the same invention, actually. Its idea is extremely simple. So this is a diagram showing that here's the diameter of our device. Red is high energy, blue is low energy, and this high energy part, when you reduce the dimension, the thickness has to be thinner and thinner and thinner. Eventually it becomes yellow and then blue. But you see, when you explore this part, small devices can give you extremely high stability. And this part, I think you can easily imagine, because after all, this is a bar magnet. When you place your bar magnet perpendicular to the plane, it magnetizes either up or down without any further anisotropies at the interface. So this is what we came up with. Of course, we analyzed many devices and realized that there's such a component. In order to understand what the behavior of them, we have to include the shape anisotropy. and then came up with this idea of making a bar magnet. And I'm very sure that you have, you know what bar magnets are, right? And it took us almost 3 years to get to this, make this bar magnet-like nanostructure. And it was, to some extent, a learning experience because we know we should be able to do it, but the repeatability and yield was miserable. Basically, on many occasions, there's no surviving devices. But very fortunately, we got a postdoc from Lam Research. He was sick and tired of being told to do this, repeat and doing this without being told why I need to do this. So he wanted to go back to university, want to go from scratch and understand the physics and the device technology and device engineering. And so he joined, and he and also this graduate student Watanabe, it took them more than 2 years, but very fortunately we succeeded in this, showing that this is the way to go. So we called it shape anisotropy magnetic tunnel junction. So this is the entire spectrum of one interface, two interfaces, four interfaces, single shape anisotropy, and interface plus shape anisotropy. And we are very sure that we can go down to at least, we haven't made an array of them, but single devices, we can go down to below 3 nanometers. Okay, for the interest of time, I'll skip this part, but basically you have two choices, including many interfaces or just using one bar magnet. It gives you different characteristics, and here we can switch it faster. Here the stability is there, and there's a review paper if you would like to go into the details of this. All right, and the good thing is that we have not changed the material system that we are working on. And that is good for tool set makers because they don't have to develop new tool machines for at each generation. So that was good too. All right. Now let me go into probabilistic computing. This diagram I showed, and which means that I can manipulate the energy barrier, making it larger than large so that we can make it stable, but at the same time we can make it unstable. And so by reducing this barrier height, we can make our magnetic tunnel junction very unstable. So this is up and down, parallel and anti-parallel state, but it jumps back and forth in each, let's say, several milliseconds now. So we can design this. And utilizing this characteristics, we showed that we can build probabilistic computer. Back in 1981, Feynman, in his famous talk, he said, if you want to make a simulation of nature, you'd better make your computer quantum mechanical, and that's quantum computing. But at the same time, he also said the other way to simulate probabilistic nature of nature is by a computer itself is probabilistic. And here he also suggested probabilistic computer is a way to go, or is a possibility. So we built integer factorization. But basically, this is an optimization problem. Here, the energy function is such that given your integer, and we need to find two integers that the product of which is equal to the given integer. And this, we implement things in such a way using this unstable magnetic tunnel junction and feedback system, which we borrowed, algorithm which we borrowed from adiabatic quantum computing to make sure that we can find the lowest energy combination of X, Y. And this is how we got it. Using 4 p-bits, we can factorize 35. Not terribly impressive, but I can do it myself. 6 p-bits, 23 times 7, and 945. This, it becomes slightly difficult, but still doable. But this one also shows that 945 is 63, right? 63 times 15. Okay, so it works, and people have gone to many bits and currently, but the good news here is that it's asynchronous, so it allows parallel operation of a large number of p-bits. And it can also emulate a certain class of quantum circuits that, for example, assigning 10 to 100 p-bits to 1 qubits, we can emulate a class of quantum circuits. So that's good. It's a cheap man's way of doing quantum computers. It also can do other things like this is a recent, or it's almost 10 months old, but the spin circuit for generative AI. In a generative AI, people want to have this random number distribution of this Gaussian type, and we showed that we can generate in a very economic way. So here, the transistor count, we can make it 3,000 times less, and energy efficiency is 150 times greater. So that's good, great news. So many things we did for proof of concept. I told you combinatorial optimization, machine learning, quantum simulation, and generating Gaussian-like random numbers. But so with relatively small number of qubits. But the catch here is that it's extremely slow because each random steps were somewhere around 1 millisecond. And we need to make sure that to be able to improve it orders of magnitude, hopefully 6 orders of magnitude to make it compatible with other technologies. So we looked into this setting, which is physics of nanomagnets, reduction of time scale for large scale problems. Yes, indeed. And naturally, the energy barrier has to be low. That's true, but that's not good enough. We found because we can tweak this tau naught, and that has to be done simultaneously in order to get a very fast random telegraph noise in that regard. So we started with simulation. It's the same energy barrier, E over kBT of approximately 4 or 3.8. And other parameters, this is perpendicular and in plane. They're all choosing the parameter almost the same. It gives us basically the same result as expected, nothing fancy. But in reality, in-plane magnetic tunnel junction have very anisotropic potential. Remember that in the very beginning, I showed you yellow arrow and red arrow, and things like that. And that also comes into, in order to represent those very difficult to make it perpendicular is parameterized by this HK effective of 1 Tesla. When you include this, the behavior is very different. And so basically, your perpendicular magnetic tunnel junction has a potential landscape that is smooth, which makes your magnetization dynamics slower. But because of your confinement in plane configuration is steep, your magnetization fluctuates much faster. Well, basically, it has a narrower quantum well in a sense. It's easy to understand in that way. So, following this idea, we decided to show that indeed we can do this by constructing in-plane, this time in-plane magnetic tunnel junction with small energy barrier and large anisotropy. And we found that indeed we can go down to 8 nanoseconds. So almost 6 times faster variation. So that's good. So how good this might be? And if you want to compare this sampling throughput, how many flips per nanosecond, we can do 10 to the 6 nanosecond flips. And how much power consumption do you need compared to other GPUs and TPUs? They need much more energy if you want to have this very high throughput. But this is projected ones using this 8 nanosecond magnetic tunnel junction, but we should be able to do these things at much lower power consumption. So how to implement this is not a straightforward matter, but in principle, we can reduce the power that they're using by orders of magnitude by this approach. Okay, the last one, antiferromagnets for the future. So let me just spend my last 3 minutes on this. I've been talking about ferromagnets, and it's the resistance change given by the change in this configuration or magnetization is quite large. So we have been using this to read the state of ferromagnets. But as I mentioned a number of times that there's a stray field associated with it. And eventually, when we want to densely pack those ferromagnetic devices, it interferes each other. So it starts interfering somewhere around 10 nanometers in our case. So natural thing is to go to antiferromagnets, because after all, it doesn't have magnetization, macroscopic at least. But collinear antiferromagnets, they don't exhibit change in resistance. So we cannot read it, or we can read it, but it's extremely difficult. But there is another class of antiferromagnets called non-collinear antiferromagnets, and they have a band structure in such a way that they exhibit a large anomalous Hall effect. Ferromagnets also show large anomalous Hall effect, but it depends, and it's proportional to magnetization. But this one has a band structure effect, and these two configurations, band structure-wise or magnetization-wise, it's the same, but they give us a very different response in terms of anomalous Hall effect, which was first shown by Nakatsuji of University of Tokyo back, it's already 10 years ago, I believe. And so using this, we might be able to build a very nice new generation of magnetic random access memories and other memories as well, or just some other functions as well. So we first showed that indeed we can manipulate the state by applying current in this direction and using spin orbit effect to inject spins into this manganese 310. And we see that there is a certain region where we see a response of these rotating spins in the system. But in this case, we used a big polycrystalline layer, and they almost all averaged out. But at a certain point, we see the trace of this chiral spin rotation. And that was a difficult time to convince the referee that this is indeed chiral spin rotation. So we compared it with calculation or simulation, but there are diehard referees, and we struggled for some time. But this time we made it into a dot, and we showed that indeed running or putting in spin polarized or spins, injecting spins can change the state from one state to the other. And good news is that you can actually do it a number of times without failure. This is 1,000. So and the speed is also 100 picoseconds, 0.1 nanosecond, right? So 0.1 nanosecond. So speed is much faster than ferromagnet as well. So just to give you an example, here, this 0 to 1, so half a rotation. Here we have 2 rotations, and so on. So this is a map that we've been plotting out. Okay, so this will be my last slide. It's interesting to note that the physics are different. For ferromagnet, transfer of angular momentum is to just transfer it, and it changes your state. But in antiferromagnet that you have seen, it starts internal motion, which means that it behaves like as if you have an inertial mass. So the physics are different as well. Okay, I think I used all my time. So this is what I have covered, and I'm not going over them once again, but impact of spintronics, non-volatile memory, physics and scalability of magnetic tunnel junction, probabilistic computing with stochastic junction, and antiferromagnets for the future. Sorry.